Good afternoon, everybody, and welcome to today's lecture on quantum technologies. It is very heartening to see so many of you here today, day when there is India-Pakistan match, and in fact, attendance in our Sky Theatre, it has reduced a bit. In spite of that, I'm seeing almost a full hall. Thank you very much. This gives us a lot of encouragement to keep going. And as many of you may know, Jawaharlal Nehru Planetarium conducts various programs throughout the year for popularization of science and non-formal science education. We are just through with our busy season where our summer vacation time, lots of visitors were there, over some 75,000. And we had 12 different workshops for students from 4th, 5th standard up to undergraduates. Some of our science popularization activities are our Sky Theatre shows, exhibitions, monthly programs, sky gazing programs, and in fact today we have our monthly science movie. We also organize programs on special occasions, and the upcoming event is Asteroid Day on June 10th. This is to create awareness about threat posed by near-Earth objects to Earth. We will be having a poster exhibition, a workshop for high school students, and a public lecture by a very distinguished scientist, Professor J.N. Goswami of Physical Research Laboratory, Allahabad. Details about the events are available on our website, and also we have put some posters. I invite you all for this lecture. Today we have a distinguished scientist, Dr. Aditi Day of Harishchandra Institute, Allahabad, to deliver this lecture. I extend a very warm welcome to you, madam. I welcome you all, and I request Dr. Day to speak few words about ICTS. Thank you.
Welcome, everyone. I wanted to say a few words about ICTS, though all of you may be very familiar with ICTS already. Just a few words. ICTS, as you know, ICTS is a part of the TIFR system. It is a research institute in the north of Bangalore, and we have 3 mandates: in-house research, programs, and finally outreach. In programs, we have scientific programs in all areas, physics, chemistry, biology, mathematics, and so on, conducted all the time throughout the year. And our last mandate, the outreach, we conduct a few lectures, Einstein lectures, many public lectures are held, and of course KAAPI with Curiosity in conjunction with JNP. All our talks are archived in ICT. Most of our talks are archived in ICTS Talks. You have to just go to the YouTube channel and you can see them at your leisure. So today it's my great pleasure to introduce Professor Aditi Sen Dey. She is a faculty in physics in Harishchandra Research Institute, Allahabad. She is well known for her research on quantum information and computation, QIC as it is called, quantum communication and quantum cryptography. She and her husband Ujjwal have built a very strong group in quantum computing in Harishchandra Research Institute. She has received the Shwanti Swarup Bhatnagar Prize for Science and Technology in 2018. She is the first woman physicist to have got this award. Congratulations, Aditi. So it is a great honor for us to have her here to give this talk. She'll be talking on quantum technologies today. Before we start, I would like Professor Pramod to hand her a small little memento on behalf of ICTS.
Good afternoon, everyone. I thank Rukmini, Rajesh, and all the members at ICTS and Planetarium to give me this opportunity to speak in this program. This is a very nice program. From time to time, I watch in YouTube. Now I'm really happy that I'm part of this program. Really happy to participate in this program. Okay, so I'm now going to tell some of the area in which I work for last almost 20 years. So, as it is written, I'll be talking about technologies. So, in this 21st century, we all are dependent on different technologies. We use every day some technologies to fulfill our need. But in my talk in next 1 hour, I will try to convince that if we build technologies based on quantum physics, that will be much more efficient than the ones that we are using nowadays. So the two technology I'm going to talk about, one is computer, like desktop, laptop, and so on. And I will show you that if we build a quantum computer, that can solve certain problems which we are not able to solve in our normal computer like desktop, laptops. Then I will talk about certain communication devices. And usually communication devices are broadly classified into two categories. One is communication without security, and another is secure communication. And this is actually known as cryptography. So I will also tell that if you use quantum physics or quantum laws, you will get certain advantages which you cannot get in our current communication, from our current communication devices. Okay, so let's start with the first one, the computer. Okay, so the computer that we use, this desktop, laptop, tablet, or whatever, these I call classical computers. Okay, so okay, we know from our everyday experience that they are useful. And if I go on, then we should tell that they are not only useful, but they are very useful for different reasons. Okay, so what can we do with this laptop desktop? First of all, we can type certain document. Okay, then we can listen music. Okay, or we can watch movies. And then we also can surf internet, which are probably very important nowadays to gather information. But then also we do certain things, like we do calculations. So we actually use computer to solve certain mathematical problems. So usually in the classical computer that we use every day, the basic unit is the bit, that is one of the zeros or ones. And how it works, we give certain input, and input is usually translated in bit. So certain array of zeros and one. Then computer manipulate by performing certain gates, which I am not going to discuss, and gives us certain outputs in terms of bits. So this is the basic way our normal computer work. Now let's consider certain mathematical problem that I have talked that computer usually solves certain mathematical problem. So the first problem that I am going to talk is the prime identification problem. So I will give you a number and you have to tell me whether the number is prime or not. So, okay, if I ask you the prime numbers till 1 to 100, then I think probably in this room all of us know what are the prime numbers. Even my daughter who is in class 6 now know what are the prime numbers. And suppose I go on, I ask that, okay, I ask you the prime numbers till 1000. Then also you will be able to tell me with some effort that what are the prime numbers. But now suppose I give you a 10-digit number. Okay? Actually, I typed randomly this one. Only I was careful that the last digit should be an odd number. So I put it 3. And now I ask you that, okay, tell me whether this number is prime or not. Now it's not so easy, right? Because you have to find out that there is no factor which is 1 or this number itself. And so it will be, you have to write a computer program which can tell us at the end of the running of the program whether this number is prime or not. Okay, so I can check, and actually it's not a prime number. It is divisible by 7. So the question that we ask is the following, that can you design a program in a normal computer which can tell me that whether a n-digit number is prime or not, any arbitrary n-digit number. So here I put 10, you can say 125-digit number or any digit number. You have to tell me, and I have to write an efficient program so that at the end of the program I will be able to answer with a reasonable time that this number is prime or not. Now, actually this looks such a simple problem, but it was unsolved for a long time, and it was solved in 2002 by 3 computer scientists from IIT Kanpur. And so they proposed an algorithm, and they show that by their algorithm they can solve or they can identify whether a number is prime or not within a polynomial time. Now, whatever I was talking about the reasonable time, that reasonable means mathematically with polynomial time. So if you have an n-digit number, then the number of steps taken in the algorithm should be of the order of n square, n cube, like that. So then I call the polynomial time. And so this is they are the people who solved this problem. So this is good news that, okay, it was unsolved for a long time, but there is our desktop, and by our laptop we can write down a program by which we can solve this mathematical problem. Now let's consider another problem, which is quite related but a bit different. It's a prime factorization problem. So now I give you an integer, and you have to tell me prime factors of that integer. So suppose I give you 45, this is a 2-digit number, and you know the prime factors is 5 and this 3 square. Now suppose I give 72, then these are the prime factors. So we can do that. We can do it in hand, or we can do it in a computer. So now again I type 8-digit number, but this time I was not so clever, so I write an even number. And so I know at least 2 is one of the prime factor, but my aim is to find out all the prime factors of this number. And okay, one has to think a bit, because this is an 8-digit number, and okay, this is possible because although it has a factor 17. So more you grow, the factors are more prime numbers, it will be difficult, as you can understand. But these are the prime factors of this number. So this is an 8-digit number. Now I become more ambitious, and I tell, okay, I give you a 125-digit number. Okay? Then you can just search in the Google, and you will be able to find this data, that if you work with almost 1600 workstations, then to arbitrary 125-digit number, it may take 8 months to solve this problem. And if you have a double the digit, that means 250-digit number, then it may take years, which is unreasonable. It's almost the age of the universe. So what we understand that till now, there is, if we kind of formulate this question a bit mathematically, so we can see that if we give you an n-digit integer, then to find out the prime factors of this n-digit number, In a classical computer, whatever algorithm you write, it usually takes exponentially n steps. So it is not possible to solve this problem till date. This is important, that it is not possible to solve till date with a polynomial time. Because it can happen that tomorrow some people may solve, but till date there is no efficient classical algorithm available. And so this was the news, and so at least we identify one problem which we cannot solve in our normal computer, and not only normal computer, but even a most powerful computer in the world we will not be able to solve. And then the quantum mechanics plays an important role, because in 1994, USA mathematician Peter Shor showed that by using quantum mechanics, you can solve this prime factorization problem in polynomial steps. That means in a reasonable time. And this is probably the first example where people have shown that it is important to build a quantum computer. So this is Peter Shor. Later on, there are more algorithms proposed, for example, Grover's search algorithm, Deutsch-Jotz algorithm. In all the algorithms, a main message was given that if you use quantum mechanics, then you can reduce the steps that is involved, that are required in classical computer, in our normal powerful computer. Here I just want to mention one thing. This was actually motivated by one of our friend who also told this in her talk, and I also got kind of motivated to put this slide. So suppose I want to build a better and better lantern, or a better and better candle to get the light. This is not a substitution. This will not lead to the electric bulb. So there is a revolution in technology. Better lantern, better candle can give us a better light, but it will not lead to the electric bulb. So this is really a technological revolution. So similarly, making a better and better classical computer, which we see in last probably 50, 60 years, that we get a more sophisticated, compact, efficient computer, that research is also important, but that will not lead to the efficiency that we get in a quantum computer. Because the classical computer is based on the different physics, and quantum computer is based on quantum physics. So this is, as we know, this cannot replace that. So it's a kind of revolution in technology that one has to build quantum computer. So just since I will be talking about quantum physics, so I just, okay, in my entire talk, it is not required that one should know quantum mechanics or something. You can, just for completeness, I put some slide. So we know that the quantum mechanics, actually by quantum physics, describes the properties of microscopic particles like atomic and subatomic, and it was kind of formulated in 1920s by famous scientists Einstein, Schrödinger, Heisenberg, Dirac, Bose, Born, et al. And this et al. Is important because many important scientists I missed, and including all the experimentalists. So they contributed, formulated the quantum physics that we learn now in textbook. And so probably this is the famous picture that you have seen. This is the conference where they said that most of the quantum physicists who has built quantum mechanics were present. So the basic things that I require is the following. So in quantum physics, any situations that I want to describe in a physical system that is associated with the vectors in a linear space, and this linear space also include the angle defined. So it should also include the concept of angle. So a linear space in which angle is defined is known as Hilbert space. So we can think of the two-dimensional complex Hilbert space, and so if I want to represent spin of an electron, that means that will be a vector or the element of the complex Hilbert space. So this is one thing I require, and that actually helped me to build the basic unit of quantum computer. So as I said, in a classical computer, the basic unit is bit, which is one of them, zeros or one. So any input have to be translated in terms of zeros and one. Now in a quantum computer, the basic unit, that will be quantum bit, in short QU bit. And what is that? This is an arbitrary, qubit is an arbitrary two-dimensional quantum state. And it can be represented like that, and where this up and down is the up and down spin of a spin half particle. This alpha, beta are complex number. So geometrically, if we want to imagine that what is qubit, you can think of a sphere where the poles are up and down, then the surface of the sphere, all these points represent the qubit. So any arbitrary two-dimensional quantum state can be thought of as they lie in the surface of this sphere. Now the important ingredient that are important to build this quantum algorithm is the superposition principle. So what is that? So cat plays an important role, as you know, in quantum physics, at least many of you. So cat can be alive. And at the same time, in the classical world, we also see independently, although sad, but cat can be dead. So quantum mechanics tells us that there exist states which can be represent alive plus dead together. And this actually is the superposition principle, and this actually lead to the qubit or the quantum bit, which I just show that it's alpha up plus beta down. And this is actually the main or the key success of Shor's algorithm. Of course, as I said, it's quantum mechanics which leads to this Shor's algorithm, but it also the superposition principle which lead to the this Shor's algorithm or the efficiency that we got to solve the prime factorization problem. So now the question is, okay, it's in 1994, then is it only theory? Theoretically already it has been shown that it is powerful. Now what about experiment? Now there are some experiment. So for example, this is the roadmap which was published recently, which said that they are trying to build this in next 20 years or so. And there are many technological giants or companies are involved, like Google, IBM, Microsoft, which you also probably hear in newspapers. In particular, the small scale quantum computer has already been built. And for example, the maximum number of qubit based computer which was built is Google's 72 qubit computer. And if you are interested, you can find lots of websites where also there are IBM quantum computer which is available in the internet, where you can even run certain program and you can also implement certain algorithm if you wish. That's a 16 qubit quantum computer. Okay, so now I come to the next part. So this is the communication devices. So I will talk about certain aspect of communication devices without security and also certain aspects of secure quantum communication. So we all know, we all use several communication devices which help us to communicate each other. So these are the mobile phones, now e-book chapters and so on. And probably I am from that era where we use this kind of telephone or the television, radio. Also I should say I am from the era where I used to read newspaper. Now people read e-paper. So we also use an important thing which nowadays are going to miss, because now we send emails to communicate. In our time, we used to send letters to communicate each other, and post office plays an important role. Okay, so this post office was the medium. So any communication process should involve at least two parties. One is Alice, another is Bob. And they are in two different locations, two distant locations. So suppose Alice is in Bangalore and Bengaluru, and Bob is in Allahabad. And they are not together. This is I am not discussing. And typically, Alice is the sender and Bob is the receiver. So this name, this can be Ali and something, Bobby or something, the Indian name, but I use because this is from the classical cryptography. This is typically they use, and so somehow in quantum information science they also adopt. So now I change a bit, so they can be sender as well as receiver in this time, and if you are again in the old time, so I don't know how many people know, but they are the artists from Bengal, quite popular. As I said, in any communication process should involve two parties, and Alice's task is to send some information to Bob. Now suppose Alice wants to send that Alice now is in Varanasi. Okay? So any communication process also should consist of few steps. So the first step, that Alice wants to send this information Varanasi to Bob. One way is just write down Varanasi in a paper and post it. Now if Alice doesn't want that, so Alice can, instead of sending Varanasi, Alice wants to send this. And if you look carefully, these are not just random alphabets, but these are some rule. Can you guess it? Yeah, exactly. So this is 2 letters, so 3 steps forward. So instead of sending Alice Varanasi, Alice now sends this to Bob. So the first step in any communication process is encoding. Now the second step, that is Alice sends it via optical fiber or some horse rider, we don't know, but with some medium. So this is the sending, the second step. Now the third step is Bob receives it, and Bob also understands like you that how to decode the message. Okay? Then only Bob will be able to decode and get the message that Alice is in Varanasi. Okay? So as you see that any communication process consists of 3 steps. 1, encoding, second, sending, and third is decoding. So any communication process usually can be characterized by these 3 steps. So now if I come back to this scenario, so Alice wants to send certain information to Bob. Now as we understand that the information can be classical or quantum. What do I mean by that? Classical means that Alice wants to send certain bits to Bob. This is a classical information, as I have told you. Any classical informations can be translated into bits. And in case of quantum, Alice wants to send certain quantum state to Bob. Now quantum state, as I have told, for example, Alice suppose wants to send qubit to Bob, any 2-dimensional quantum state to Bob. So this is one example. So now I will be considering or concentrating, or I will be discussing this quantum state transfer, how we do this. So as I told that in quantum mechanics, situations in our physical systems can be represented by a vectors or elements in the Hilbert space. Now I need another concept, that is that if I want to describe 2 or more physical systems, then I have to consider the tensor product of the individual Hilbert spaces, which is denoted by that. For example, if I have arrays of electron spins, which usually are how we represent the solids, then to represent arrays of electron spin, we have to consider product of several Hilbert spaces. Now, with this in mind, we can now consider the question that how we do quantum state transfer. And this is a quite well-known concept known as quantum teleportation. So it was introduced in 1993 by these 6 people. Now, as I said, Alice's aim to transfer an arbitrary quantum state to Bob. For example, we can consider arbitrary qubit, 2-dimensional quantum state to Bob. That means Alice's aim is to send this state mathematically to Bob. Now, what about classical device? Suppose I don't want to use quantum mechanics, but I want to transfer quantum state. Then how many bits we require to encode this to send this arbitrary quantum state? Now, as I said that any arbitrary quantum state can be a point in the surface of the sphere. You can think like that. So, you understand that to encode any points in the surface, you need infinite number of bits. And so, if I don't use any quantum physics, but I want to transfer quantum state by using bits, I need infinite amount of classical communication or infinite amount of bits. Now, ask the question whether we get any advantage if we have some quantum mechanical state at hand. So, Alice, as I said, Alice has certain state phi, which is the input state, and Alice's task is to send this input to Bob. Of course, you can tell that, okay, I put it in a box, I send it, I go and I give it to Bob. This is one possibility. So, now this is not allowed, that I cannot put it in a box and just give Bob as a gift. So, Alice wants to send this arbitrary quantum state to Bob, not where this physical sending is not allowed. So, how to do it? To do that, Alice and Bob should a priori build a bridge between them. Now, this bridge is not the normal classical bridge, but the quantum bridge. Okay? And this quantum bridge can be represented by like that. I will talk about the properties of the bridge later on, but I just want to first show that whether that bridge is worth studying, then only we can think of defining, studying and so on. Let's see whether this bridge can help us to get certain advantage or not. This is first thing that I want to show. So, suppose you believe me that, okay, this bridge is possible to build in the quantum world. So, the people who probably studied physics knows that this is a 2-spin half particle, they are in a singlet state. Now, Alice performs some quantum mechanically allowed measurement on her particle of the bridge and the input state that she poses. Alice then, after measurement, sends her measurement result to Bob. So, sending measurement result to Bob means 2 bits of classical communication to Bob. And then Bob performs certain unitary operation and recovers the state. So, if I now compare the classical and quantum device, then I see that in case of classical device, to fulfill this task, Alice requires infinite amount of bits or infinite amount of classical communication. On the other hand, if Alice and Bob a priori share a quantum state, a priori build a bridge, then only 2 bits of classical communication is enough to send this qubit. So, you see that infinite resource reduction by using this quantum state or by using that quantum bridge. that I have talked. So this is the quantum teleportation protocol introduced by in 1993 by these 6 people. Now, of course, the next question is that people now are interested that, okay, it's good that you can send quantum state from Alice to Bob. Now, I want to connect to many people. So there will be many senders, many receivers, whether you can do the similar task or not. And yes, actually you can do. And there are a lot of work going on in this direction. And in our group also we have done some work, which I am not going to discuss, but it leads to the network that we want to build. So now the way I have presented, it looks like there is some magic going on, or there is something. Alice and Bob is preparing some bridge and doing something. So it's not. The main ingredient, of course, is quantum mechanics. And we understand that these properties of the bridge or the bridge has certain property which help to meet that or to have the task. Now this bridge or the property is known as something called entanglement. And this is the key ingredient that plays a crucial key ingredient for quantum teleportation. And this is the concept which actually plays an important role in entire quantum communication and quantum computational tasks. This was developed by several people. If you are interested, then there is a nice review paper by these 4 of them. They are the Horodetzky family, and they have also play a key role to develop this theory. We have also written certain review paper, which I am not going to discuss. So let's discuss what is entanglement, or what is the property that bridge has. So Alice and Bob, they are situated in 2 different locations, 2 distant locations. Now suppose Alice prepared certain quantum mechanical state in her lab, and Bob prepares certain quantum mechanical state in his lab. Then actually the joint state looks like that in a tensor product Hilbert space that I have talked. So if a state, or if Alice and Bob will be able to prepare certain states even when they are far apart, then these states are unentangled states or the useless states for the communication that I have described. So to prepare, so the useless or the states which are not useful for quantum information protocols are those states that Alice and Bob will be able to prepare even when they are situated in 2 distant locations, 2 different cities, for example. And mathematically, the useless states are like that. So for example, they can prepare spin up of an electron and spin down of a spin up particle. This is the example of useless states in quantum information, for quantum information processing tasks. Now, if the entangled states are those states that Alice and Bob will not be able to prepare when they are situated in 2 distant locations. So to prepare entangled states, 2 particles should interact, and then only they can prepare these states. They cannot do certain things in their own laboratory, or they cannot do certain things independently and prepare this state. It is not possible. So one can think that there is a source which prepare. They have all the machinery where the 2 particles interact in certain way by following certain Hamiltonian, and then source send 1 particle to Alice and source send another particle to Bob. This state, which also lies in this tensor product Hilbert space, is called the entangled state. And one example of an entangled state was the state that I have used for quantum teleportation. And the entangled state mathematically cannot be written like that. Now, with the definition, it seems that it's quite easy to show whether a state is entangled or not. Just to tell you that given a quantum state, it is still very difficult to prove whether a state is entangled or not. It is still an open question for arbitrary quantum mechanical state. Now, it's also not theory. It is, there are a lot of experimental progress for this. For example, if you consider a physical system like photons, and if you consider the polarization degrees of freedom of photons, then right-handed and left-handed circular polarization is a good candidate or the ideal candidate for a qubit. And in that scenario, by using polarization degrees of freedom, people have already prepared entangled state, and they are able to prepare entangled state by other degrees of freedom of photons as well. For example, the teleportation that I have described, there is an experiment few years back. So this is the Spain and this is the Africa. So there are two islands called La Palma and Tenerife. So they are 143 kilometers away, and the Austrian group led by Anton Zeilinger, they showed that they can perform quantum teleportation between these two islands by using photons. So you can see that that means in teleportation they have to first create an entangled state and then they have to perform teleportation. So they can create entangled state between two island which is 143 kilometers away. So if you look that, if we now think about the Indian setup, so between Allahabad and Varanasi is 130 kilometers away, you can prepare entangled state. If you look Bangalore and Mysore, it's also possible to create entangled state as well as quantum teleportation. But at least in 2016, the few years back, it was impossible to do teleportation experiment between Bangalore and Hampi, for example, which is around 350 kilometers away. Now, in a breakthrough experiment which was done in China recently, where they show that they can create entangled state in a satellite and then they distribute entangled state in two cities which are 1200 kilometers away. And this was led by Pan's group, and this actually is kind of breakthrough in quantum communication, where they show that they can overcome they can perform a experiment, quantum communication experiment for a large distance, which actually makes it now possible to do a teleportation experiment between Bangalore and Mumbai, for example. So this is now a reality. So not only the physical system photon, but by using ions, also one can do experiment. For example, the internal levels of ions can serve as qubits, and they can trap ion and they can do certain experiments. For example, as far as I know, this is the highest number of qubits they can entangle in ion trap, which is 20 qubit. And this is very important for performing quantum computation, or this is one of the first steps to build quantum computer, because also we may need a highly entangled state between many qubits in case of quantum computer. So this is the maximum number of qubits they can entangle. There are many other potential systems, physical systems available, where one can build quantum computer or where one can do quantum communication task or the entangled states. One is ultra cold atoms in optical lattice. There are NMRs, semiconductor devices, and probably now the most interesting device or interesting systems coming up is the superconducting qubits. So I have some time, right? Yeah. So I just want to say, so that it's a very important question that one has to find a proper physical systems in which quantum computer can be built, or quantum communications can be implemented. In other words, where entangled states can be found. And there are a lot of work going on around the world, and also we have done certain work in our group, including a review paper where we have shown that what are the physical systems that will be important to build a quantum computer. So now another thing that, so as I show that in case of quantum state transfer, entangled states are important. Now I am not going to discuss in details, but if I want to send classical information like bits, if I encode the bits in quantum states, then also one can show that quantum mechanics help. And this I am not going to discuss, but one can show that the encoding by using quantum states can be done in a smaller system if you use quantum device compared to classical device. And this is important because this is also related to the resource that you are using. So in classical device, encoding can be done in a higher dimension. On the other hand, if you use quantum device, you need a smaller system or you need a smaller dimension to encode your bits, classical bits. And this protocol is known as quantum dense coding protocol, and which I am not going to discuss. It's introduced by Bennett and Weisner. And also we have done some work which is actually helped to build the quantum internet that probably is one of the main challenge that people are thinking. So now I come to the last part where I'll be discussing about the secure communication or quantum cryptography. So what is the difference between the communication that I have described and the communication that I am now going to describe? So here the aim is to, Alice wants to send some classical information, but now securely. So what do you mean? That is, there is a sender Alice, there is a Bob, which was also before, whether I send classical information or quantum state transfer. Now there is a third party, which I called eavesdropper. So the third party aim is to gather as much information as possible that Alice is sending to Bob. So now third party, we have to encode our message in such a way that third party cannot gather information from the when I am sending to Bob. So I have to make my message, or I have to encode now more cleverly. So this is the eavesdropper that I thought to put, and probably now things have changed, right? Okay, so what are the usefulness of quantum communication or the secure quantum communication? And so if I take out the quantum part, that the secure communication has lot of advantages that we nowadays use. For example, if we want to use internet banking, then of course I don't want that my password is known to the third party. So I have to, so whenever you, probably all of you have experienced that whenever we type a simple password, they said, okay, no, you use the block letter, you have to use certain mathematical number, you have to use certain this hash, question mark, @ dot dot dot, some special characters. So that means that our password should be such that it should be known to the bank and me, not to the third party, even not to my friend, right? So I have to secure in this way. When I do the shopping via internet, the same thing. And this is also related to the national security, because suppose there is, okay, it's not expected or it is not required, or but there is suppose a war going on, and then the commander wants to send some information to the soldiers, then commanders of course have to ensure that this information is only sent to those soldiers whom he wants. because if it is known to the opponent party, it will be dangerous. So it's of course in a simple-minded way I describe, it's not so simple, and of course probably we don't want war, but still it's important for national security. It is, I mean, the cryptography has been used for a long time, even in ancient time when the kings are fighting. And probably the most one we have heard is in the World War II, where the cryptography was used. And there are a lot of stories we know. So the current cryptography system is, the security of the current cryptography system is based on the belief that some mathematical problem cannot be solved in our normal computer or even in a powerful classical computer within a polynomial time or within a reasonable time. Now you can already guess that one of the problems that I already discussed, that these prime factors of a given integer, which we know that cannot be solved in a powerful computer. If the number of digits is huge, say 125 digits, then of course the eavesdropper will not wait 8 months to find out the factors and then break my internet banking password. It's not possible. So it's so the security of the current crypto system is based on this kind of belief, and this is actually lead to the security of all the communication, internet banking to national security. Now the twist of this whole story is the following, that I have already discussed that if you use quantum mechanics, then that mathematical problem can be solved within a polynomial time. And that means that all the crypto systems that we are using currently will be insecure if one builds quantum computer. So if one has a quantum computer, all the current crypto systems will be insecure. So that's a kind of threat, right? So if someone builds a quantum computer, all our internet banking and everything will be insecure. So what is the remedy? Again, quantum mechanics help, because there is a crypto system now has been built where the security is based on the validity or on the principles of quantum mechanics. So, and it was shown that this crypto or this cryptography based on quantum mechanics is secure even when quantum computer exists. Even when you build a quantum computer, there is an alternating crypto system which is a quantum based crypto system which remains secure even when you have a quantum computer. And this was actually proposed in 1984 again by Bennett and Brassard, and then Arthur Eckert in 1991. So in this new quantum based crypto system, instead of sending bits from Alice to Bob, you now send randomly generated quantum states to Bob. And due to the superposition principle, we also have non-orthogonal states in quantum mechanics, which helps you or which gives you the power that quantum crypto system will be secure even when you have a quantum computer. And interestingly, the laws of quantum mechanics also ensure that if there is a eavesdropper, there is a third party, then this eavesdropper cannot get any information without disturbing it. So without disturbing quantum system, eavesdropper will not gather any information. That means if eavesdropper wants to gather information that Alice is sending, and eavesdropper wants to do anything, then Alice and Bob will understand. And if Alice and Bob can understand, of course they will not continue the game. They just stop and start another protocol. Okay? So in that way, actually quantum mechanics ensured that, and this was proved in a paper by Utters and Zurek in 1982, which tells that copying of arbitrary quantum state is not possible. That means the quantum Xerox machine doesn't exist. So in a quantum world, there is no Xerox machine, and the kind of extension of that theorem says that disturbing any quantum mechanical systems can be detected. So this theorem is important to get the security of quantum cryptography. So these are the Bennett, Brassard and Eckert. So this is also not theory. Actually, quantum cryptography is very well developed now, and it also kind of commercialized. And for example, in the Football World Cup at South Africa, what they did, they used these quantum crypto systems to send or to encrypt certain link between Durban's stadium, from Durban Stadium and some joint operation center. So they have some, they have tested, and also they tested in the Geneva election between the mayor of the city and the certain centers, voting centers outside the city center. So this was actually this group which was which has done, and even if you search in the web, you will find that you can buy even a quantum crypto system. But then the question is why we are not buying. We are not buying because there is no quantum computer. So there is not yet any challenge that someone breaks our crypto system. So of course this quantum crypto system is still just showing that quantum mechanics help to encrypt messages, but still there is no threat because there is no quantum computer in the world. Okay, so it's this is some work also we have done where we also provide a bound on security secret key rate recently, and then there is some concept which called monogamy of quantum entanglement or quantum correlation, which tells that if Alice and Bob is highly entangled, then eavesdropper cannot gather any information from Alice and Bob. This is an entangled based quantum cryptography which was introduced by Arthur Eckert, and we have done also some work and also some book chapter. If you are interested, you can look. Okay, with this I come to the end, so I try to kind of convince, I don't know how much you are convinced, but I try that quantum mechanics can revolutionize our computational power and our communicational ability, and these communication capabilities can be with or without security. In both the situation, quantum mechanics help, and quantum devices are important to build. So if I kind of try to think what is the status of quantum technology, because this was the title of my talk. So quantum cryptography, as I have shown you, it's already a reality. Now people are trying to build quantum internet, that means the communications between several senders, several receivers, just like the current classical communication where we are all connected either via internet, mobile, etc., etc. So this is the, by using quantum mechanics, can we do that? This is the one of the aim which we are trying, and probably last one is to build the quantum computer. This is very challenging one, but there are lot of efforts going on around the world where people are trying to build quantum computer. Some small scale one is already a reality, but hopefully there will be a computer with a bigger, involving bigger number of qubits. So this is the more or less the QIC group at HRI. There are some members who has left. So we are around 20 people working, many PhDs and postdocs, and we there are 3 faculty members, Arun, Ujjwal and myself. If you are interested to visit and know more, don't hesitate, please write to us. We have visitor program throughout the year. You can write to us, visit us, and thank you very much for your attention.
Thank you, Aditi, for this wonderful talk. And I hope lectures are going to be still continued even in the quantum era. It was a wonderful thing. And if are you willing to take some questions?
Yeah, of course.
So have some water or something. So any questions? There are 2 mics on the both sides, and if you have any questions, please ask one by one. So the first question is there.
I guess I was just asking, the real advantage of quantum computing, I suppose, would possibly come in combinatorial problems, where using the quantum principle because of the wave function thing and the linearity and superposition thing, can reduce the, we can use classical calculus, which is not possible otherwise in a normal combinatorial setup. Would that be, one example?
Yeah, if I understand correctly, so yes, the linearity or the superposition principle of quantum mechanics help you to reduce the steps. But I just want to mention that the way I have presented, it seems that it's so simple, but there are still certain problems, mathematical problems still unsolved. We don't know whether it will be solvable by quantum computer or not. Just I want to make this comment.
Second thing is, you said that no cloning, but for quantum teleportation, for any teleportation you need cloning, no?
Cloning?
Cloning. You need to clone a state of an object to some other place. Oh, you have to destroy it here and then, okay, there is no cloning.
Exactly. So yeah, that's a very important question. So the quantum teleportation, how they presented in a newspaper, it seems that there is a Alice who performs a measurement and Bob gets the state. It's like a signaling, right? But there is no violation of signaling, neither there is a violation of no cloning theorem. Because when Alice performs a measurement, the original input is destroyed and Bob gets the state after the communication. And since after the communication, after these 2 bits of classical communication from Alice to Bob, Bob performs some unitary and recovers the input state. So there is also no superluminal signaling. There is no violation of relativity because you need these 2 bits of classical communication. Otherwise, one can show that Bob's state has no information. It is actually a half I. So it's an identity operator, has no information about the input state.
One more, sorry, so in entanglement, if I can understand, if I think about a n-dimensional cube, so instead of all the n raised to, n possibilities, the entanglement reduces the possibilities to a restricted manifold because of the relations, right? Okay. So that's what makes computing faster.
Yeah, but again, I just want to make comment. It's not yet proven that it's a understanding or belief again that entangled states help to give the power in quantum computer, but it's still not proven rigorously mathematically that entangled state will always help to get the power in quantum computer.
So it reduces the number of possibilities.
Yeah, it's true. This is just our understanding.
Any other questions? Yeah, lot of questions here. So once again. Can you talk in the mic, please?
In this teleportation, the distance of 130 kilometers, why it is restricted to 130? What is the, is it some kind of sensitivity detection or, line of sight or whatever reason? So,
although I am not experimentalist, but I can try to answer the question. They do this experiment at night in free space because, of course, the long distance cannot be done by optical fiber. So photons do not interact with the other particles, and that's why it's important because it doesn't decohere or it doesn't lost so quickly. But this is also a problem that you cannot create entangled state so quickly. And also at night when you do this experiment, hardly you can detect photons coming, and detector can detect that. So if your distance is high, then or it's long, then there is a less possibility to detect photon. So this is the same problem they also faced when they have a 1200 kilometers. So you can check in their, it's also in the website that they have to wait a huge, time to really prove that they are able to do this 1200 kilometers. But there are, of course, these technological difficulties which people are trying to overcome.
So what's the time they have to wait?
Long. I don't remember exactly the time, but it's long. Few days probably they have to be. Few hundred millions probably photons coming then only.
Ma'am, thank you for a very nice session. I'm a layman, so this session was nice for me to also understand what's going on. I have a question. I work in software product development, and currently I'm working on building a product for routers. So we have to put all the secure communication into the product also. Now we are also developing a feature called lawful intercept, where it's a mandatory feature where we have to allow the government to lawfully intercept calls which are, from a terrorist point of view or something like that. Now, if we go to the quantum space and you're saying that you can't intercept it without changing the information, how will such a feature be possible in future when, quantum computers come out?
Yeah, here there are things that I have described due to time. It's all are kind of ideal situation. Of course, you can disturb, but still you can carry certain information. You understand there is a eavesdropper, but if you have to always discard that possibility, then there are a lot of loss of bits and so on. So when you have an intercept strategy, then you allow certain type of threshold above which you discard your protocol and below which you just continue your quantum crypto system. Now in case of quantum computer, if it comes, then this classical crypto system will not be secure anymore. So surely it has to be replaced by quantum crypto, but there will be still there can be an attack, and that is exactly what they tried with this Geneva election and this. They forcefully somehow intercept the bits and try to gather information. They want to see that how much the system is robust against this attack. So I think there are, as I said, that ideal situations are proven, but still there are several loopholes which are there, which has to be addressed. Like all the security proofs are still are given or proven.
Ma'am, if for example a gramophone, in a gramophone, or at least how a bit is physically stored as a 0 or 1 from magnetic needle traditionally. So is there a way to analog storage, is there an analog storage equivalent for quantum information, or at least a wave function?
Yeah, there is. This is called quantum memory, but it's very difficult because these entangled states look beautiful, they give a lot of advantage, but they are very fragile towards noise. It also depends on on which physical systems in which you create entangled states. So there are a lot of work going on in quantum memory where people are trying that how long the states can live. Okay, and there are a lot of experiments going on. In INTRA, for example, in 2017, I think, there is a report that where they show that they can create an entangled state which can live 1 minute, which is huge. So you can understand that 1 minute is huge, but of course it will not serve our purpose. Like if I buy a device like storage device that we buy and it says that okay, after a minute it's gone, we will not buy, right? So people are trying to get this, and there are a lot of open problems, but this question has been people are addressing this question, but it's
so ma'am, the hypothesis I was trying to state was, could you just store any wave and use it to represent?
Look, ideal situation you can, but there will be any storage medium is important that it is robust against any decoherence, any noise. This is what I want to say. That's the important part of any storage device. If you buy a storage device which gone wrong, you just connect to your desktop, then of course you will not buy from that company. So it's same like quantum case. Ideally you can store. I am theoretician, I can store many minutes, many hours entangled states, but experimentalists will not believe me. Right?
Yeah. There are two parts of my question. Richard Feynman says if you think you understand quantum mechanics, you actually don't understand quantum mechanics. I'm an electronics engineer. So the part that excites me is how would one build a quantum computer? It is seen that from Google's quantum computer and the IBM Q, there is a lot of power requirement that goes into this. How would this, as in the future, would be a sustainable, become a sustainable computer? Would quantum computers be used in day-to-day life?
Okay, that's the main challenge, I think. That's why you see that the roadmap that they show, they say 2035 probably they want to build, but I think that's also the challenge. So this is the main thing, that they can do 72 qubit quantum computer, but 72 qubit quantum computer is not enough to show that this is powerful than the classical one. So as you know, there are many reports where they said that they can factorize 15. Now this can be just a tabletop experiment, right? I say that, okay, I build a computer where I can factor 15. Then you said, okay, I can do it in hand, or I can do it in, even if it's a 150, then you can do it in your mobile. So why should you build a quantum computer? Now quantum computer really, to show the power, one has to build a many qubits computer, which is much more than 72. It's kind of 1000 qubit quantum computer required to show their power, around 1000 or more than that. So for that, this is the people, I think there are a lot of technological challenges as well as some physics breakthrough has to be done so that we can reach that.
The second part of the question is that we have been through a paradigm shift of information theory. We have seen binary, and now we see quantum. Will we ever hit a singularity where there is no point there we are going anywhere? Is there a singularity? Singularity where there is no point of advancement.
Okay, it's I don't know. I mean, okay. I mean, at this point, probably we all, with the experiment and theory, we all believe quantum mechanics, and we all believe the postulates of quantum mechanics, and based on that, we are trying to argue. Now, what? I don't know.
Yeah. So.
Yeah.
Hello, ma'am. Suppose we use quantum entanglement and we transfer the quantum state from point A to point B, and for a person in point B, in order to read that quantum state, isn't the measurement going to affect the quantum state of the system or state vector of the system? How are we going to do that?
No, the point is that as I told that actually this B doesn't know what state it gets, okay? So in quantum teleportation experiment, suppose there is some state, this alpha beta neither known to Alice nor known to Bob, okay? So it just shows that Alice performs some measurement and then Alice sends to Bob, and Bob only has the state. Now what is the exact value of alpha beta is not known to Alice neither to Bob, okay? So of course you are right that if I want to know alpha beta, then I have to perform measurement. Even in that situation, single copy is not enough. I need infinite number of copies to get this alpha beta. This is, they are not talking in teleportation protocol.
Yeah. So continuing from all these three questions here, Yaman.
Yeah.
So is this there is no error control in it, like entire our communications theories and whatever the storage is based on the error control mechanism starting from Shannon's theory to here. I just want to know that do we have any error control mechanism will be in the future?
There is. So there is a error correcting code.
Yes.
So there is a quantum error corrections also, which are quite developed. So when I said there were 1000 qubits will be enough, that without quantum error correction.
Okay.
And if we actually also want to include quantum error correction, which has to be included because there will be noise and there will be also some decoherence, then you need more number of qubits.
But how do you decide what was the correct state?
No, I mean that is that also based on, actually the quantum error correction is also based on entanglement.
Okay.
So it was also built and it's also quite developed, which so quantum computer along with quantum error correction is complete.
Right. Thank you.
But there are a lot of also open problems because it's a kind of developing stage.
Thank
There
you.
is,
This is regarding quantum communication. Yeah. You had said that I think moment somebody intercepts who's not somebody else, then there is a way, it means immediately the entire transaction can be stopped. So that can it be made null and void, or whatever is already transferred, will the other person be able to use it?
No. That is what I said, that ideally what I said is correct, that if the quantum mechanics or quantum mechanical postulates ensure that if there is an eavesdropper and eavesdropper wants to gather any information, then eavesdropper actually quantum mechanics gathering information means you have to measure, and whenever you measure you disturb the system, and if you disturb the system, Bob can immediately understand that their system is disturbed, so they can discard the protocol. But in that way you actually lose lot of bits or your effort. So the problem that whatever I have described due to time is the ideal situation. Of course there is a threshold people usually study where even if you intercept, still Alice and Bob can continue up to certain level so that this crypto system will be secure enough, and if it go beyond that threshold you have to stop.
My question is on the other side. I understand that part. Like, it's a very confidential information which I'm passing on. So I'm more than happy to destroy the information in toto rather than somebody else looking at the data. Is that possible in this scenario?
Destroy the information.
Right. So that I may live without information rather than it falling into the wrong hands. If something like that is possible?
So what you are saying, that the eavesdropper wants to destroy the information?
No, I'm saying A and B are communicating, C is eavesdropping. Moment they know that C is eavesdropping, you are saying the protocol will be stopped, and then C will discontinue to, C cannot continue to hear what is happening with A and B. Is it possible that whatever is already a data, which is already eavesdropped, can it be destroyed?
Yeah, I think. I mean, you just says you stop the protocol. You just discard all the bits.
Even the already information passed on will also get destroyed.
Okay, so a small thing which probably I haven't described properly due to time. The point is that in quantum cryptography is not really cryptography. It's a quantum key generation. So you actually share in this way the identical key between Alice and Bob even without meaning.
Okay.
And then you use one-time pad to generate or to send the message. So in this, the protocol that I have described is actually sharing identical key between sender and receiver, which they use to share information. So message is not shared. So this is the good part of the quantum cryptography.
there is one question from the viewers. What is more efficient, ion trap or superconductivity qubit?
That's a very tricky question. Okay, so I think that superconducting qubits are coming up is one of the potential one where people want to build the quantum computer. On the other hand, ion trap has already established where there is a entangled state they can create, which is between 20 qubit and so on. So I think there is some kind of competition, and also I think that at the end probably there will be a need that two types of physical system may come together to build one thing. So you are not sure, we are not sure, I think. It's not so, I think, black and white.
Yeah. Any other questions?
Yeah, ma'am, here. Okay.
There's one.
When Alice had the aim to have an arbitrary qubit transfer, you mentioned that in the Brock sphere there would be infinite sets of data for the classical scenario. Why would you need infinite sets of data with the classical?
No, because, okay, it's analogously you can think this alpha 0 plus beta 1, it's analogous, it's just geometrically you think that this is any points in the surface of the sphere. To encode any points in the surface of the sphere, now you forget about quantum mechanics. Any point in the surface of the sphere, there are an infinite number of points in the surface of the sphere, and you need infinite bits to encode, and that's why I said.
Sure. Thank you.
Yeah, okay. Ma'am, now quantum entanglement is a form of communication. We can use it as a form of communication. Is that right? Yeah. So now how fast is this form of communication? Is it faster than optical fiber? Is it slower? What is the actual speed like?
Okay, so here we are talking about the advantage of, I mean, we still don't talk about this fast thing, okay? So the speed we are not discussing in my talk, or also it's not commonly discussed. It just shows that what advantage you get in the encoding process. So sending also depends, so as I said, in the communication there are these 3 steps. So encoding, sending and decoding. We are mostly talking about encoding and decoding. Sending depends on the physical system that you are using, okay? So if you use quantum communication based on photons, probably use optical fiber or the free space. Also in case of massive particles like atoms or ions, you also can use free space, or you trapped in cavities. Now they also do that experiment. But these we are not talking. We are mainly interested in the first and the last step. And you are probably talking about the middle step, which we haven't discussed.
Thank you, ma'am.
Ma'am, can you tell about the joint measurement procedure that Alice will use? Like, what does it exactly represent and involve?
Yeah, so, okay, so that I haven't described at all. So the point is that these 2 particles perform actually the entangled measurement. And the protocol that I have described, so that protocol involves the measurement, which is actually called Bell basis measurement, which the state that I have described, this up down minus down up, you can also, because it's a 4-dimensional space, so you can have a 4 orthogonal states. You can always create, because that form the basis in any, so if you have 4 dimension, you have 4 states. So the one of the state is that the one you share, the other 3 you can construct, which will be also entangled. And this joint measurement will be in this entangled basis measurement. If you want, I can write down the mathematical form. Is there any? Okay, so I haven't written because, so if I, so I think I use, this is the state which I call singlet shared between Alice and Bob. Now you can, taking this as one of the basis state, you can create, for example, this one, and so these are the 4 orthogonal states in which Alice performs a measurement. So this is known as the Bell measurement or the entangled basis measurement.
I have a question there. Can the source eavesdrop and find out what Alice and Bob are?
Yeah, actually this is also another, I mean, you can also think that the source is itself a eavesdropper. So this is another, there are many ways you can think of a eavesdropper. One is Alice and Bob sharing something, and there is a eavesdropper, third party. You can think source is the bad person, and then you may have more complicated
like a detective story.
Yeah.
And ma'am, can you tell me about to what extent in this field of quantum cryptography and quantum communication, to what extent is in current day research in the physics part taking place?
No, everything is physics.
No, means is it like in quantum cryptography, does it involve to what extent research in the physics behind it is taking place, or is it more taking on the computational side of all these factors?
Quantum communication, whatever I have discussed, is based on physics totally.
Yes.
And of course, whenever you talk about implementation, you have to implement in physical systems and you have to understand the physical system, so it's physics. Okay. Now in quantum cryptography as well as in quantum communication, some parts are motivated by a classical information theory as well as classical cryptography. But it cannot be totally based on classical information theory, because as you understand that in quantum cryptography as well as quantum communication, whatever measurements you do, whatever operations you will do, that should follow the quantum laws. And that's the physics part always in. So, of course, you cannot just translate all the theorem to the quantum one, you cannot just apply it directly. You have to somehow translate the theory to the quantum one. Someone here mentioned about Shannon noiseless coding theorem. You have to translate that to the somehow involving different von Neumann entropy, and then there is a similar parallel theorem also exists in quantum mechanics or quantum information theory. So these only can give you the motivation.
Quantum communication is affected by time?
That I already talked. I mean, we haven't talked about the time because the sending thing we are not interested. We are mainly interested in encoding and decoding, and we only take care. I mean, in the process we understand that although we do a non-relativistic thing, but still there is no relativity breaking, like there is no superfast signaling or there is no superluminal signal. That is already ensured.
Any other questions? If not, you can join the
There is no mic.
Thanks. This is probably a very stupid question, but the whole assumption is of this no cloning theorem is based on the argument that entanglement is only possible between two particles. What about an n particle entangled system? Is there such a system that's there, or in that you could technically have a eavesdropper and not detect that?
No, the point is that n particle entangled state doesn't mean you have a clone of quantum states. Okay? Known states can always be copied. Okay? So if you have a, suppose you have, I mean, you can also think like if you know the state, you can always copy. There is no violation of any quantum mechanical law. The point is you want to build a Xerox machine which can copy the state which is unknown. Of course, I don't want to, if you want to build a classical event, suppose I want to build a Xerox machine which can copy only your certificates and not others. That's not effective, right? I want to copy, or I want to make a Xerox machine which can copy everybody's certificates, right? Or everybody's information, everybody's mark sheets. So unknown states cannot be copied. Known state can always be copied. There is no problem. So what you said, the n-party entangled state doesn't mean that you are copying the states, particles. It can or it may not. Depends on, this n-party system is very complicated. I also don't understand much.
I'm here. So thank you for the talk again. It was pretty interesting. So I work with computers all the time, and classical bits make a lot of sense. I understand they're pretty straightforward. Is there a way to understand qubits in a similar fashion, which is much easier? Like you could point me to references, people, articles, whatever.
Yeah, so there are now, I mean, the points you are interested, so depends on that. But there is a book by Nielsen and Chuang, which is actually pretty good. And there is now lots of book. Mark Wilde also has a book. So there are a lot of review also articles you can find.
Where can I find those articles?
Yeah, so there is a website, for example, there is a website aps.org, so I can write.
Yeah, that will be helpful.
There is one last question. Oh, sorry. Right, sir.
Yeah. So this is the website where physical review articles are published. They have reviews of modern physics, and and you can find a lot of review articles in this subject. But now I think Google is also the good place. You just search and you may find a good review. But the book of Nielsen and Chuang is also a good one for quantum algorithms, quantum computing. So it's called
Okay, one last question before we part for tea.
So I'm lucky for being the last question here. And thanks for such an entangling session today evening. Really good use of a Sunday. So quick question is that, like you mentioned that quantum computers are still in the making, 22 qubits is there, maybe still being worked upon, or maybe it's already there in the Google labs. Sometime back, IBM offered a beta of their cloud computing platform of their quantum computer. What is it practical, if anything, someone can accomplish using that cloud computing access?
What?
What is it something that a person can do practically? For example, maybe I can do something naive things like maybe calculating prime factors, okay, but that's not as fun, I think. I heard some time back that they were suggesting, oh, please use our cloud computing platform, but don't mess around with public classical cryptography. Don't break someone's SSL, please. So was that something which really was possible, or what are basically the things which were possible with what they were offering, IBM's beta access to their cloud computer?
The point is that the ideal situation is that you have a n-digit or a very large digit numbers and integer, and you have to find the prime factors. Then you know that the classical cryptography is insecure if you have a quantum computer. Now this will be to have such a huge digit integer prime factorization, all the password if has to be built on that basis, then it will be very costly. So usually people build on a very small assumptions. So that can be broken by even, I don't know whether it can be broken by the 16 qubit quantum computer available in IBM, but can be. Now the point is that that qubit computer is only useful to do the known protocols. You just do it there as an implementation, as a tabletop experiment, have some fun. But really whether you can use that effectively or have some really good technological, some implementation or realization you can show or not, that we still don't know. I mean, probably people are trying. Of course, they want that we use it, because if there is any fault, any decoherence kind of thing, they will be able to detect and they can change, they can modify their circuit and so on.
So what I understood is that those cloud access, which was beta access, which was given by IBM, that was good for tabletop, but not for anything.
No, you can, but we still don't know.
All right.
One has to design.
Okay. Thank you. Thank you so much.
Okay. Thank you very much for your questions. The next KAAPI with Curiosity talk is going to be on July 7th at 4 p.m., not at 3, 4 p.m., the usual time. And it's on a mathematical adventure into immunology.